Okay. So with that being said, I've got the PowerPoint open. So we talked again on Tuesday about the difference between process control and process capability, right? So this slide actually, the chapter's title is process capability, but we're going to go into process control today. And control is where you identify what the range of your process is capable of doing consistently, okay? And then process capability is where you're comparing it to your customer specifications, okay? So we're going to talk about process control specifically today. Interesting. Well, there we go. I was like, why is it not looking normal? Okay. So when we talk about a process control chart, every time we look at a chart, you should be aware that there are at least 4 components on the chart. Okay. So the very first component is going to be what's the mean of your current process, right? That's this dashed yellow line, okay? And then what's plotted around it, right, are the sample averages that you get on a daily, hourly, whatever bucket of time you're going to check that in, right? Then you plot the actual sample averages here, okay? And what you find is then you've got your control limit lines. You've got an upper control limit line and a lower control limit line. And that's what we're going to learn how to do today is how do we calculate those control limit lines for different types of processes. And we set that control limit. We use that normal distribution curve and what we understand about the space underneath it and say that it can be, if we're 3 standard deviations plus or minus our mean, we're capturing about 99.7% of all of the probable outcomes that are going to occur, okay? And so what you're doing is you're calculating that, and then you're saying, but wait, look, we're above that upper control limit here, which tells us that our process is now out of control. And if we tie that into the lecture that we had on Tuesday, there are 2 different types of variation that we're looking at, right? There's normal variation and there's abnormal variation. So as long as those sample averages fall within the upper control limit and lower control limit, we say that's typically normal variation and we don't need to do anything with it. In fact, if we do something with it, we're actually going to disimprove the process, right? Because we're reacting too quickly to issues, okay? So we're trying to monitor that process variability over time. This control chart sends us this statistical signal that says if there's a special cause or abnormal variation in play. Our decision rule then, of course, is if it's within those boundaries, the upper control limit and lower control limit boundaries, we don't mess with it. And if it's outside those boundaries, then it's time to do something about it. Okay? And so, sorry, bounced ahead. All right. So control charts help us to determine the type of variation that's present. So it's important to know because the strategies for improving a process that is in statistical control is different from what you need to do if a process isn't in statistical control. Because the first thing you have to do is get it in statistical control, and then you can work on improving it. Because if you're making changes to a moving target, you don't really know whether or not you're making improvements or not. Okay? So if a process is out of control, the discovery and removal of special causes is usually the responsibility of the frontline personnel, right? They're the ones dealing with that process. Okay? However, some can be removed only by management. It's important to remember that removing special causes from a process is not improving the process. You are merely putting the process in statistical control where it needs to be. Okay? And so how do I know if that process is in statistical control? Well, we're looking at, so you can see each of these is a different example of the control limits, right? And so the very top one, we have a stable process, and we would say that that process is in control because our average samples that we're pulling on an ongoing basis fall within those limits, okay? If you look at the next one where it says unstable, well, we have some that are both outside the limit below it and outside the limit above it. So we would say that that's unstable. There are ways, and we're not going to get into that in particular in this class, to look for trends. Did you all talk about that in your quality class? So one of the things that you can do is you can, rather than just looking at the chart, you can start to do a count of how many are below the mean and how many are above the mean. And if you get a significant number that are falling above the mean, that's going to be your clue that, okay, well, we've got something, we're no longer normal around the mean, we're starting to trend above the mean, right? Or we're starting to trend below the mean, okay? And then you can look at cyclical issues or shift issues. I mean, sometimes those are easy to see where, you know, you change shifts and different operators, different things happen from one shift to the next, okay? So as we think about process control and improvement, right, here we've got this process that's out of control. And so the first thing that we do is we have to remove that abnormal variation so the process is in control, right? And then when we improve it, what happens is we narrow up that focus around the mean so that our upper control limit and lower control limit come in tighter, right? And so that's when we know that we've improved the process, when we're able to move those control limits, okay? And again, you'll hear me say in these charts, those data points that are on there don't represent individual units of measure. They represent averages of a sample, okay? So, and that's an important statistical point, okay? So, again, they represent averages of a sample. So, for example, if you worked at Skittles, right, or M&Ms, right, and you pulled off a sample of M&Ms, right, maybe you check, maybe you're looking at and you're weighing them to make sure that they're the right weight, right? Okay, so maybe you're going to do that 4 times, and you're going to take the average of those 4 weights, and that's going to be what you plot. You're not going to plot the one weight. You're going to plot the average of those weights. Okay. So for control limits and process control, right? Again, we're back to that original slide, and we want to monitor that process over time, and we use our probability curve to determine where we want those control limits set. Pretty standard to set it at plus or minus 3 standard deviation, so then your z-score would be 3, okay? And again, we have type 1 and type 2 error, just like you do in statistical, in your stats classes, right? Type 1 is a false alarm, right? And type 2 is a missed signal. So type 1 says, I'm identifying something as abnormal that's not really abnormal. And type 2 says, I have something abnormal and I've failed to identify it. Okay, so we've got a couple of, again, that ties in with your stats classes. What we're going to talk about today specifically is that there are really 3 different types of approaches that we take depending on what it is that we're measuring. If we're measuring something that has a continuous scale, like weight, length, radius, right? Then we're talking about, we're going to use what's called the mean and the range to determine whether or not we're in control, okay? If we're doing something that you would consider to be dichotomous, does it, like a car, does it start or does it not? There's nothing in between there, right? It's either yes it does or no it doesn't, right? We use what we call proportion defective or fraction defective, and we use a p-chart for that, okay? And then on another example, maybe you're looking at something and you're counting how many defects there are, like on a piece of glass. So I'm going to look and I'm going to count how many scratches there are on that piece of glass, right? And so that's a C chart. So now I'm going to count how many issues I've got on an individual unit, okay? The concept of control limits, where we have the upper control, lower control, and mean, and plot the data points, those 4 things apply the same across all of those different types of charts, right? But how we calculate those upper control limits and lower control limits changes depending on which type we're actually working with, okay? So you should be able to answer the question, why do we calculate control limits for both the mean and the range for continuous variables? Okay, an easy example for me is let's say that I have a process that's averaging, my mean is 500, right? And as I look at my average over time, it's right at 500. So I'm thinking, well, that's perfect, right? Well, not if it goes from 1 to 999 to 1 to 999 to 1, or 1 to 1,000, right? And so, again, you have to understand both the mean and the range on continuous variables to know that you're in control, okay? And so that's why we do two types of control charts, okay? So the first one we're going to talk about is the mean, or the X-bar control limit formula. And your control limit formulas are going to look very similar from one to the other, but what changes is that second function or that second kind of term in the equation, right? It's going to be the z-score times some type of standard deviation, okay? And so in this case, we start out with, in the perfect world, we would have all the information we would need, and we would calculate the mean and the standard deviation, which are the true mean and standard deviation of the individual operations, both of which we typically don't know, okay? And so therefore, we have to estimate the mean by using the overall average of the sample, okay? So we start to replace then, instead of the mean, we're going to use the X double bar, okay? And we estimate the standard deviation by small letter s, which just means it's the standard deviation of our sample. And so a couple of things that you need to remember is capital N represents the number of random samples that you're going to collect, and small n is the number of observations in each sample. So our observation there is, or if we were looking at that, the n times n represents, I've got 20 samples that I'm drawing, and I have 5 observations in each sample, which means that I have a total of 100 observations, right? And so, again, when you use the small n, understand that we're talking about the number of, I want to make sure, the number of observations in each sample, okay? So what we do then is we replace in that formula, because we don't know the true mean and we don't know the true standard deviation, we replace them with estimates of that. And on the screen, hold on just a second. I know, I saw I had the wrong number. What I'd like to do is just, next Tuesday. All right, yeah. And then the one I type X double bar because I'm not very good in Excel at figuring out, or in PowerPoint and figuring out how to put 2 bars above the capital X, but that's really what that represents. And then, so we're replacing the true mean and the true standard deviation, which we don't know, with estimates of that, which is the average of our observations plus the standard deviation of our sample. Okay, is basically what we're after there. Yeah.
I had a question on the capital N and lowercase n.
Uh-huh.
Is that subgroup size and number of subgroups?
It's like our K and N.
Yeah. I just want to make sure that was...
Is that subgroup size and the number of subgroups? Yes.
Okay.
So capital N would be your number of subgroups.
Okay.
And small n is your...
I just wanted to make sure.
Yeah, and that's going to be the challenge, because...
Right.
And in fact, different textbooks use different variables too. So even in the operations area, so it's about understanding what those represent. Right. So great question. Great question. Okay. All right. So what I thought I'd do is, there's an example in the text, 9.6, and that example in the text is about a set of garage doors, I think, or overhead doors. So let me go ahead and get to 9.6, and I'll kind of read what that says. And what I thought I'd do is, I've got them already calculated, and I'm just going to show you how I calculate them in here, and then I'm going to post this Excel file if I haven't already. I think I may have already posted it already. Because we could spend a lot of time, you could spend a lot of time watching me create this, and I think that understanding how it's created and then having the ability to go back and look at it is probably going to be more helpful than actually watching me mess in Excel. Okay, so example 9.6 starts on page 248. So it's taking information from table 9.1, and it says that we have 20 samples. So if we have 20 samples, that's going to be capital N, right? That's the number of, did you call it subgroups? Is that what you called it? So, or the number of samples, okay, of door weights over time, each containing 5 doors, which is the number of observations in each sample. And so what we need to do with that is we need to come up with our control limits, okay? And I'm going to shrink this down a little bit. So what I've done is I've taken the information in their table and I've transferred it. So this all is, so at day 1 at 9 a.m., they drew a sample of 5 and the average weight was 81, right? Day 1 at 11, they drew a sample of 73, right? And again, so let me rephrase that. Day 1, they sampled is 1 sample with 5 doors in it, right? Day 2 is 1 sample with 5 doors in it. Day 3 is 1 sample with 5 doors in it. So what we have to do is we have to calculate, first off, we have to calculate the average of that, of each day so that we know what data point we're going to plot, okay? And so I've done that. And then we have to know the range, right? And just so you know, there's some formulas that we can use in Excel that make it easier to find the range. You can use the max function and the min function. And so I can put max and I can highlight that range and it's going to tell me the maximum value of that range minus the minimum value of that. And it's going to, then it gives me the actual quantity range in there. It's a little confusing because we're talking about Excel ranges and the actual range of the data. Okay, and so I need to have both the mean and the range of each sample. Okay, all right. And so then what I do is so I create a chart. I don't think for your assignments, I don't think I ask you to create a chart, but this is the easiest way that I have found to create the chart is to just isolate that information. So I've got the average of each sample, right? And then on my chart, I need to have the overall average of all the data. So what I do is you have to take the average of the averages, right? So I have to take the average of all of that. And I plot that. I put that over here. So I've got, there's my daily average for each sample. Here's my overall average, or my X double bar, right? And then I need to calculate my upper control limit and my lower control limit, okay? And so to calculate my upper control limit and lower control limit to put on my chart, right? Let's look at how we do that. She says as though she can find it on her spreadsheet. Where did it go? Sorry, guys. I just did this yesterday. You wouldn't think I would have forgotten between yesterday and today. I'm going to show you those formulas over here. So we have to take that average of the averages, the X double bar, and we have to say, well, what's our z-score? And in this example, we're going to do 3 standard deviations. So our z-score is going to be 3. And I have to calculate the standard deviation of my sample. And I have to know that my n is going to be the number of observations in each sample. Okay? So if I were going to come over here and if I were going to calculate that range, I'll just redo it here. Right? So my upper control limit is equal to my X double bar, sometimes spelled double, plus, right, my z-score times s divided by the square root of n. Okay, and so in order to do that, I have to know, well, what's my standard deviation of the sample? Well, Excel lets us use STDEVA as the function to find the standard deviation. So I highlight I say the standard deviation, and I do all of that original data, right? And I find the standard deviation of that original data, okay? And then I know moving forward, I'm also going to need, for when I do the range one, I'm going to need the standard deviation of the ranges. And so I calculate it by using standard deviation of that range row, okay? And so one of the things that's different when you move from one type of chart to another is your standard deviation, where you calculate it, changes, okay? So in the X double bar, from the upper control limit and lower control limit, we're doing it we're calculating the standard deviation from the original data set. When we get to the range charts, we're calculating the standard deviation of the ranges that we've calculated, okay? And so with that being said, my upper control limit then is going to then be my average of my averages of 82.5 plus my z-score of 3 times my standard deviation of the original sample data divided by the square root of n, which we said was 5, right? Because there's 5 samples in each day, right? And so my guess is, because there's a little bit of a rounding issue going on, but that's close enough for government work, okay? So that's my upper control limit, and my lower control limit is going to be, it's almost easier for me just to copy and paste, but it's that X double bar plus minus my z-score times S divided by the square root of n, okay? So it's going to be, again, 82.5 is X double bar minus 3 times my standard deviation of the original sample divided by the square root of n, right, which is 5. 2, 3, 4, 5. Just got to make sure it was 5, okay? And so then what I would do is, in order to plot it, it's just easier for me to run this series of data points with the lower control limit and the upper control limit and the mean. You look, they're all identical all the way across here, right? And then I create my chart, and on my chart I've got the upper control limit, the lower control limit, the overall average, and I'm plotting my data points, okay? And so as I'm looking at that, then it's telling me that this process is in control, because I've got my upper control limit and my lower control limit established, and all of the data points are falling within that, okay? And I find it, I'm sure there are maybe different ways to approach creating that chart, but I find just running everything all together here, because then Excel is handy enough, I can just highlight that data and create the chart from it, okay? All right, and so that's our X bar chart, right? And so, again, our average is 82.5, our standard deviation of X bar. So that's that second part of the term. So then we get our control limits, and we can determine that our process is in control. My guess is what's going to probably be most helpful is we're going to go over this, and then as you're working with the problem, you're going to have the Excel file open and the PowerPoints open as you work through the problems, because your problems are going to be one of the continuous variable, one of a P chart, and one of a C chart. So you'll do each one of these, okay? All right, so then there's our control chart, and again, we can tell that we're in control in terms of where the mean is at. And then, but the continuous variable, again, we have to do both the mean and the range, and the only thing that changes is now we're doing our control limits off of the average range, right? We're still using our z-score, but now we're using the standard deviation of the range, okay? And so what I do is I come back here, and I've got, again, our average of the ranges comes from the fact that we calculated those ranges, right? And now I'm just taking the average of what we calculated. and then I need the standard deviation of those ranges, right? And so I then use that information with that control limit formula, right? And I take the average range minus 3 times the standard deviation of the range, okay? And what happens is it becomes a negative number, but can you have a negative range? Like, no, I'm looking for people to shake their head no. You can't have a negative range, so therefore it effectively becomes 0. So you plot it as 0, okay? And the same thing then on your upper control limit, right? You're taking the average range plus 3 times the standard deviation, right? And again, I did the exact same thing here where I just create that, I'll shrink it down so you can see the bigger picture. So what I do is I just create that 1 through 20 here so that when I go ahead and create my chart, you can see that it was picking up from that data, right? And so then it makes it really easy to chart, okay? And so every chart we have has 4 elements: upper control limit, lower control limit, overall mean, and the plot of the data points, right? And so we can look at that and we can say that that process is in control, okay? And typically, it's a little bit of a circular argument at this point, right? Because we're creating our control limits based off of the process, and so it probably ought to be in control because that's where we created that from. But you have to start somewhere. And then now you're going to move forward over time, and you're going to say, does it still stay within these limits or not? Okay? And so that's something to be aware of, right? We can look at this and tentatively say the process is in control, which is maybe not fair because we calculated those control limits off of the same data that we're testing. Okay? So you have to start somewhere to set the data points and the upper control limit and lower control limit. Okay? All right. And then there's our range chart, and it is in control based on what we calculated, or our process is stable. Okay. The next type of chart that we want to talk about is what's called a P chart, so a fraction defective. Okay. And I'll swap this out. Oops. Did I do something, Miranda?
Yeah, I printed these notes off like a while ago, and it's not the same PowerPoint, so...
They're all there, it's just maybe slightly different order.
Yeah, I'm trying to find it.
Yeah, and I think I added just a little bit in terms of what's on the P chart one to just make that a little clearer.
I can't even find that one right now, so we'll get there.
Okay, so your P chart, again, is about the fraction defective. And so it's like, does the car start or does it not start? They're yes or no answers or dichotomous variables is what you're looking at with the P chart, okay? And they're, really pretty formulas, right? It's the average P bar minus Z times the square root of P bar times 1 minus P bar divided by N. That sounds just a fun formula to say, right? P bar, P bar, P bar. Okay? So let's talk about how do we calculate P bar and what does that mean. Okay? And so we move forward kind of with that same example data set. And so we've got these doors, and so basically, instead of taking the weight or instead of taking the range of those weights, we just count how many of those doors are defective, right? And so what they've done is they say, okay, well, on day 1, there was 1 door defective. On day 2, there were 0 doors defective, right? And so I'm counting how many doors are defective in each sample. And then to calculate my P-bar for that day, it's actually the proportion. I take the proportion that were defective. So it's going to be 1 divided by 5, right? So to get to my P-bar, I have to get the proportion defective for each day, and then I'm going to take the overall average of the proportion defective, right? And so there's an extra calculation in here to go from, I have to take how many were defective, and then I have to create that into a proportion defective for that day, okay? And so then after I calculate for each day what's the proportion defective, then I take the average of all of those proportion defective, and that's my p-bar. Okay? So what we're calculating here, I think I started out to say that's p-bar. That's not correct. That's the proportion defective for that day. P-bar is the average of all of those proportion that were defective. Okay? Are you tracking with me, Abby?
How did you get to 0.2 in that row?
Because there's one defective, and there were 5 doors that we tested, so it's 1 divided by 5 tells me that my proportion defective is 0.2. Okay. And you can think of that, if it makes it easier, think of it as the percentage defective, right? Proportion defective or percentage defective. So 20% of my doors were defective on day 1, 0% on day 2. And overall, right, my average proportion defective was 0.2. So now I'm going to plug that into this formula for my upper control limit and lower control limit, and I'm going to take 0.2 plus my z-score of 3 times the square root of 0.2 times 1 minus 0.2 divided by n, or 5, right? So it's a matter of understanding what the variables represent in those formulas, right? And so the only thing that's really new in this formula is the p-bar, okay? Because we already had used the small n, right? We already know that our z-score for this particular problem was 3, okay? So then I calculate my upper control limit, and I calculate my lower control limit, and you can see it goes negative. So practically speaking, we have to plot it at 0 because it can't be negative, right? You can't have a negative proportion defective. We're not better than 100%. Okay? Does that make sense? And then, again, we're doing that same thing where we're plotting that, okay? And it looks a little funky because we get down here and we're at 0. That's actually a flat line. It just doesn't show up very well on this particular chart, right? And then this is right on the mean. And you can see that the process is considered in control because we're not outside of those particular lines. All right? Does a proportion defective make sense? Okay? All right. And then the last type that we're going to look at is the C chart. And so then, again, in the PowerPoint, we've got the formulas for peak control limits, and then there's the P-bar control chart. Okay, for C charts, we're going to use that when an item or service may have multiple defects. So the example from the text is that the overhead door company tracked order processing errors over the last 12 months. Okay, and so then what they do is, right, we just have to change a little bit of our formulas. Okay, so our standard deviation is no longer, again, that's what's changing in each type. And so now we're going to be able to estimate our standard deviation is going to be the square root of the average number of defects that we count. Okay? And so our upper control limit, this actually is probably one of the easiest control limit ones that you're going to calculate, is the average number that you find the count plus your z-score times the square root of that average count. Okay? And so if we were going to go back to Excel, so we've got the 12 months, we've got how many errors they did for each month, right? And so I need to get my average errors. And so all the way out here to the right, I calculated my C-bar for my average errors as I just took the average of all of those. And then my upper control limit is basically that C-bar plus 3 times the square root of C-bar, right? And my lower control limit is C-bar minus 3 times the square root of C-bar. So again, relatively easy. And I plot both of those, right? And again, my lower control limit can't be negative, so I plot it as 0. And then we can look and we can see that we would consider the process to be in control based on that information, right? So I think that that does a pretty good job of at least getting you a good overview of those different types of charts, the P charts and the C charts, right? All right, a couple of notes on the Canvas homework. When we talk about Z-scores, we're saying that 3 basically is equal to 99.973% of your probable outcomes are going to be within those control limits. One of your homeworks says, I think, 95%, and so the Z-score you want to use for that is 1.96, okay? And then again, I just wanted to remind you that to calculate the range in Excel, you can use the max and the min functions, right? And so your homework is just going to be about calculating these control limits and determining. You don't have to plot, right, to determine if your process is in control. If I weren't going to plot on Excel, how would I make my decision about whether or not that this process is in control? Let's say this goes away. Maybe it'll go away. It does not want to cooperate. Okay. So let's say I can't see this. How can I determine based off of this information if this process is in control without plotting it?
You could just look at the error count and see if it's above or below.
Right. So what I'm going to do is I'm going to look at the data that I would be plotting and see if any of it rises above or falls below what my control limits are. So you don't have to plot. I did in these examples because I wanted you to visually see it. But if you can just look at those and make that decision. You don't have to actually go through the plot.
So for what we submit for Canvas, we're actually just doing a table then,
Yeah.
not
Yeah.
the okay.
Mm-hmm.
Not the
And I
graph.
think I'll double check, but I'm pretty sure I put the data out there for you on Canvas so that you don't have to copy and paste from Canvas, because sometimes that doesn't work as smoothly as what we'd like. Yeah, so here's your Canvas homework 9B template, and so that has all the data in it. So all you have to do is use the data and to calculate your control limits and go from there. Okay, and then what I would do, what I've done in my solutions that I've posted, is I've just copied and pasted into out of Excel into Canvas just the table, and it just copies in as a table when you copy and paste from Excel. Okay, so that actually works pretty slick, I think. All right, and so that's going to cover it for today. And what we're going to do on next Tuesday is we're going to start to talk about process capability and how we calculate that, which is exactly what the two of you were talking about your exam. I think your most recent exam in quality. So that being said, I'm curious. So I'm going to go ahead and sign off on here.